Hello everyone. Thank you for attending the BAS Electrochemical Webinar 2023 Autumn. I'm Miho from International Sales Team, and I will be the moderator. Today, it will be the 8th lecture of a series of lectures in the field of coordination chemistry and electrochemistry, introducing basic electrochemical methods and applications. Focus on organic complexes, introduced by Professor Masa-aki Haga from Chuo University. Today's theme is Coordination Chemistry and Electrochemistry, Electrochemistry of Corrosion.
Good afternoon. This is Masa-aki Haga. Today I'm talking about the electrochemistry of corrosions. Corrosion is a problem that occurs with all metals in our surrounding, and it becomes a major issue for the corrosion protection in our infrastructures. Today I would like to talk about this corrosion in this seminar on how to evaluate corrosion rate of metals electrochemically and how to prevent corrosion by coating. Here's the list of my seminar which I have talked so far, and today I talk on electrochemistry of corrosion. I did not include electrochemical impedance spectroscopy, which will be talked later. I focus on the electron transfer kinetics, such as Butler-Balmer equations and Tafel equations. Corrosion is known to have a significant impact on our social life and industrial processes. Corrosion causes serious damage to infrastructures from pipeline, bridge, and building to vehicle and ships. On materials, corrosion causes loss of tensile strength and ductilities. The global cost of corrosion is estimated in 3 to 6% of global GDP and amount of $2.5 trillion per year. The reported serious example caused by corrosion has listed here. The first example, which is shown in the slide, these pictures, the collapse of the Italian road bridge in 2018 at Genoa, near 40 people died. The bridge was before supported by iron steel suspension bridge, as shown before. However, the suspension part were corroded and collapsed nearly 700 meters. The second accident was reported in a ship. The ship was locked in a storm on the sea, broken in half and sunk. This is believed to crevice corrosion of the joint holdings the ship together. The third example is the pipeline and reactors in the chemical plant were corroded and poisonous gas was leaked and killed 1,000 people in India. So, to tackle against corrosion will be continuous and becoming big issues. With regarding to understanding electrochemistry of metal corrosions, the contribution of Russian-born Professor Marcel Fouvet is significant. Known as the Fouvet diagram, he studied many metals and compiled these data in a book entitled Atlas of Electrochemical Equilibrium in Aqueous Solution. This book has become the Bible of corrosion chemists. Two persons in the photo, one is the Prof and the other is Professor Evans, who also contribute the electrochemistry of corrosions. In most corrosion events, the oxidation of metals in the presence of water takes place through the two electrochemical reactions, both occurring at the same metal-aqueous solution interface, as shown in this scheme. There are two electrodes, one anode and one cathode, located almost adjacent side at the junction of electron and ionic conductors. On the surface of iron, for example, iron dissolving to iron 2 react with oxygen to form iron 3, which precipitate as iron hydroxide or iron oxide. This is anodic reactions. On the other hand, a cathode reaction proceeds in which protons are reduced to generate the hydrogen or oxygen reduced to the water. These reactions at two nearby locations are considered to proceed due to electron transfer through the metals, because the metal is the conductors. Here the presence of water is considered nearly to compensate for the dissolving ion transfer outside the metals. A corrosion system can be regarded as a short-circuit electrochemical cell. Therefore, by measuring the potential current curves of the metal electrode, we can measure the polarization curve against corrosions. At first, we should consider the basic electrode kinetics, which describe the exchange current at a heterogeneous metal-electrode interface. Since corrosion is generally a slow reaction, the best way to measure electron transfer on a metal surface is to measure the potential current curve of metals by electrochemical measurement. Because of slow electron transfer rate, we can ignore the mass transfer. We obtain a polarization curve for metal corrosions. First, let us consider the electron exchange in a heterogeneous system at the electrode as a current. At the interface, reduction rate, which is cathodic current, is defined by equation 1, and rate constant Kc. For the oxidation, anodic current is given by equation 2. The difference between the cathodic and anodic current is the net current, as shown in equation 5. When the net current flows, the cell is not in equilibrium. This kinetic behavior can be described by the free energy reaction coordinate by transition state theory. At the equilibrium, free energy for both reactant and product is the same energies. When the potential is changed by delta E, the potential curve moves down as shown in this figure. We can consider the activation energy change, which reflects on the reaction rate. Considering the standard free energy change at the reaction coordinate by transition state theory at the electrode reactions, when the overpotential is applied to the electrode, what kind of change occurred at the reaction rate? The equilibrium J0 is equal to JR and the net current J0. When the overpotential applied and reached some dynamic equilibrium at the transition state, both anodic and cathodic current are given by equation 1. At the crossing point at the transition state, we introduce the transfer coefficient alpha, which is measured of the symmetry of energy barriers. Normally, this alpha is 0.5. And also, at the surface, Nernst equation established. From 2 to 3, equation 2 to 3, we can obtain the exchange current density. Equation 5 is called current over potential equations, also called Butler-Balmer equations. The first term is the cathodic component current at any potentials, and the second term given the anodic contribution to the current. The last equation in the previous slide is the famous Butler-Balmer equations. This equation holds when the solution is well stirred or current are kept so low, and mass transfer effect was not included. The photo shows the Professor Butler and Balmer. Professor Balmer is German physical chemist, the successor of the Nernst at Technische Hochschule Berlin, and not only for electrochemistry but also he contributed to the development of photochemistry. Stern-Balmer plot, which provide the photophysical intermolecular deactivation process quenching light constant at the excited state. Butler is English physical chemist at University of Edinburgh and later moved to biophysical chemistry field. In the case of large overpotential applied at negative or positive potential range, in Butler-Balmer equation, one of the bracketed terms becoming negligible. Therefore, exchange current density becoming these simple equations. Taking logarithm on both sides of these equations lead to the equation 1, which is known as the Tafel plot, a plot of log current density versus overpotentials provide useful information about the exchange current density and transfer coefficient from the linear region, called Tafel slopes. Tafel found this equation from experimental result in 1905, which is rationalized later by Butler-Balmer equations using transition state theory. Here is the current over potential curve for the iron and hydrogen system. When iron corroded by acid in aqueous solutions, anodic corrosion reaction takes place as shown in equation 1. On the other hand, the reduction process in the absence of oxygens is shown in equation 2. The net current, which is measured in polarization study, is the sum of the positive current from metal dissolution and the negative current from the proton reductions. When these two currents sum become zero, this potential corresponds to the corrosion potentials. When the logarithm of current density versus over potential gives Tafel plot, as shown here. In the absence of current supplied, as in the corrosion event, electrochemical reaction can occur only at that point, where the two lines intersect, because at that point, oxidation current and reduction current due to the two reactions is equal. The intersection point serves to identify the corrosion potentials and current. For the corrosion potential measurements, the test metal plate is used as a working electrode, which potential is regulated by the reference electrode by using logging capillary. Using the three electrode system as shown in these pictures, linear scan polarization at a scan rate less than 1 mV per second is applied. The current obtained is plotted as the logarithm scale versus potentials. There are two graphical presentations for Tafel plot, vertical or horizontal. By extrapolating the anodic regions and cathodic regions, the intersection point corresponds to the corrosion potentials and corrosion current density. Here is a case study of anti-corrosion of stainless steel by coating from the literatures. The corrosion potential of bare stainless steel on the Tafel plot was shown in black line, and the corrosion potential is minus 0.823 volt. The Tafel plot shows the coating on the mixture of superhydrophobic perfluorosiloxane and polyaniline epoxy resin, which is a combination of various materials. Using AI, shifted the corrosion potential to the more positive side, and at the same time, the corrosion current can be significantly reduced. This indicates the corrosion protection effect is significant. Many steel sheets are plated with zinc as the anti-corrosion treatment to inhibit ion oxidation by sacrificial corrosion protection, in which the zinc itself first corrode. There are two types of galvanized steel sheet: hot dip galvanized steel sheet, which have the thicker zinc coating layers and a high scratch resistance, and the electrogalvanic steel sheet, which have the thinner galvanic layers and are easy to process. However, since it is difficult to increase the thickness of the galvanized layers, chromate treatment is generally applied. While chromate coating has excellent barrier properties and self-healing capabilities, the hexavalent chromium in the film has a negative impact on the environment, and regulations are being tightened. Therefore, new corrosion preventing methods are being actively studied as an alternative to chromate treatment. While various anti-corrosion methods using polymers has been reported, a new anti-corrosion method using graphene, a carbon materials, has recently been reported. This method focuses on the chemical resistance and high two-dimensionality of graphenes, and used graphene as the anti-corrosion materials by depositing on metal surface using CVD method. In fact, it demonstrates high barrier properties and chemical resistance to oxygens. However, the CVD deposition of graphene requires vacuum conditions, which makes it difficult to scale up the process. Our laboratory has found the cuticle has excellent absorption abilities on metal surface among various organic substrate. Therefore, we focus on the dopamine which contain cuticles and work as a strong absorbent on the oxide surface of muscle. Furthermore, by adding APTEs, which form a BAS network structures when complex with dopamine, we aimed to efficiently absorb graphene oxide and reduce this film to improve the anti-corrosion effect by taking advantage of hydrophobic nature of reduced graphene oxide. Here is one example of Tafel plot our sample. One-sided oxygen reductions and zinc oxidation current at the positive potential regions. The intersection obtained by extrapolating of the straight line is the corrosion potentials and corrosion current density. From these results, we create this graph. With the horizontal axis represent the difference in corrosion potential between the solid zinc steel and the covered zinc steel, and the vertical axis represent the difference in corrosion current density between before and after the zinc steel. The larger the positive difference in corrosion potentials, the better the corrosion protection performance, and the smaller the corrosion current density, the slower the corrosion rate. In other words, lower right side of the graph show better corrosion protections. Here is a list for the corrosion challenge towards a sustainable society. These challenges for anti-corrosion will build a climate-resilient energy systems and infrastructures and bring long-term research directions, the invention of new anti-corrosive structural materials. So there are a lot of space to develop science of corrosions. Here's a summary of today's talk. I introduce you the Butler-Balmer equations and Tafel plot and how to estimate corrosion potentials and the corrosion current through this Tafel plot. Here is a reference, and 1 and 2 is the standard textbook. So you can read it. Thank you for listening.
To Professor Haga. If you have any question regarding to the lecture or other topics, you can contact us. In addition, the movie of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news. Also, you can watch the Professor Saga's past 7 lectures. The next webinar is already scheduled for December 6th. For today, thank you and have a nice week.